On January 13th, astronomers spotted something that shouldn't have been visible, a comet so far from the Sun that every previous discovery says we should never have seen it. Every detection record for this type of comet just shattered, and the scientific community is scrambling to understand what they're looking at. This isn't just another icy rock wandering through space. This is something different, something unexpected, and it's raising questions that astronomers didn't think they'd need to ask. Stay with me for the few minutes, because what we're about to explore together isn't just about one comet. It's about a cosmic mystery unfolding in real time, a journey that could lead to one of the most spectacular celestial displays in 60 years, or it could end in a dramatic flash of vaporization. Either way, we're witnesses to something rare, something precious, and I want to help you understand exactly what makes this discovery so extraordinary. What makes this comet different from every other one we've found? Why are some astronomers already whispering about the greatest show since 1965? And what happens when something this massive dives straight toward the Sun's corona, where temperatures could melt steel in an instant? We're going to answer all of those questions, but first, we need to understand the impossible moment that started this entire story. Picture the scene. Astronomers scanning the deep reaches of space, doing what they do every night, searching for objects in near-Earth space, tracking known comets, cataloguing asteroids, routine work, the kind of patient observation that rarely produces surprises. Then, on one screen, a faint smudge of light appears where nothing should be bright enough to register. At first, there's hesitation. Is it real? Could it be an artifact? A glitch in the imaging system? Some distant galaxy mistaken for something closer? But as more observations roll in, confirmation arrives. It's real, it's moving, and it's a comet. They assign it a temporary designation while they gather more data. 6AC4721. Not a poetic name, not something that rolls off the tongue with wonder, just a catalogue number that will do until they understand what they've found. But within hours, as astronomers compare notes and run calculations, excitement begins to build. This isn't just any comet, this is a sungrazer, one of those rare objects that will dive dangerously close to our star. And here's where everything gets strange. Sungrazers have been discovered before, dozens of them over the years. Scientists know what to expect. They know these comets typically remain invisible until they're much, much closer to the Sun, when solar heating begins to vaporize their ices and create the glowing atmosphere and tail we associate with comets. The pattern is predictable. Sungrazers hide in the darkness until they're practically on the Sun's doorstep, then suddenly blaze into visibility as they approach their fiery destination. That's how it's always worked. Except 6AC4721 didn't follow the script. When astronomers calculated how far away this comet was at the moment of discovery, they found themselves staring at numbers that didn't make sense. It was visible from a distance where other sungrazers had remained completely invisible. Not just slightly farther, dramatically farther. This comet was shining brightly enough to be detected when it should have been nothing more than a frozen dark chunk of ice and rock lost in the vast emptiness between planets. Now, if you've been fortunate enough to follow space discoveries over the years, you know that astronomy is built on patterns. Scientists observe, measure, catalogue, and over time those observations create expectations. When something breaks the pattern, when reality refuses to match what decades of experience say should happen, that's when you know you're looking at something genuinely unusual. And that's exactly what happened here. Think about it this way. Imagine you're trying to spot a candle flame in the distance. During the day, you might see it from across a room, maybe from across a yard if conditions are perfect. But could you see that same candle flame from miles away? Of course not. The light simply isn't strong enough to reach your eyes with enough intensity to register. Now, if someone told you they spotted a candle flame from 10 miles away with their naked eye, you'd immediately know something was wrong with that story. Either they didn't actually see a candle, maybe they saw something much larger, like a bonfire or some other explanation exists that breaks your understanding of how light and distance work. That's the situation astronomers found themselves in with 6AC4721. They were seeing light from a distance that should have made it invisible, which meant something about their basic assumptions had to be wrong. And in this case, the most likely explanation wasn't that physics had suddenly changed. It was that this comet was far more massive than any sungrazer they'd previously encountered. You see, a comet's brightness at any given distance depends primarily on two factors: how much surface area is being heated by the sun and exposed to sunlight, and how actively that heated material is releasing gas and dust. A small comet might be a few hundred yards across. When sunlight hits it, only that limited surface area can reflect light back to Earth. It's like the difference between shining a flashlight on a golf ball versus shining it on a beach ball. The beach ball reflects more light simply because it's bigger, even if both objects are made of the same material. So when astronomers saw 6AC4721 from that impossible distance, their minds immediately went to size. If this comet was visible when it should have been dark, then it must be enormous, not just slightly larger than typical sungrazers, but potentially one of the biggest objects of its kind ever discovered. And that realization sent ripples of excitement through the astronomical community, because size matters in ways that go far beyond simple visibility. A larger comet means more material, more mass, more gravitational self-cohesion. It means an object that might actually survive the hellish journey through the sun's outer atmosphere, when smaller comets would be torn apart and vaporized. It means the potential for a truly spectacular show if conditions align properly. But it also means higher stakes, more uncertainty, and a cosmic drama playing out on a scale that captures imagination in ways that smaller, predictable objects simply cannot. Now, I want you to understand something important about how astronomers work, because it matters for everything that follows. When they make a discovery like this, they don't immediately jump to conclusions. They don't start announcing that the comet of the century has arrived. Instead, they gather data. They take measurement after measurement, night after night. They compare their observations with colleagues around the world. They run calculations, build models, check their work, and slowly, carefully, piece together a picture of what they're actually seeing. And as that picture emerged over the days following January 13th, the excitement grew. Because every new observation confirmed the initial impression. This comet was indeed massive. Its trajectory calculations showed it was on a collision course with the sun's corona, calculated to make its closest approach in 75 days. And if it survived that approach, if it managed to hold itself together through temperatures that would vaporize most materials instantly, then Earth-based observers might witness something truly extraordinary. But I'm getting ahead of the story. Right now, standing at the moment of discovery, astronomers were just beginning to process what they'd found. They had a comet that shouldn't have been visible, which suggested remarkable size. They had a trajectory calculation showing it would dive toward the sun, and they had a date circled on their calendars, April 5th, the day this cosmic visitor would face its ultimate test. What they didn't have yet was certainty about any of the outcomes. Would it survive? Would it brighten dramatically? Would it put on a show visible to the naked eye? Or would it disappoint despite its impressive size? Those questions remained open, and in many ways they still remain open today. Because comets, for all our scientific advancement, remain stubbornly unpredictable. They're ancient objects, leftover building blocks from the formation of our solar system, and each one carries its own unique composition, its own structural quirks, its own personality in how it responds to solar heating. So when you hear about this discovery, when you hear astronomers expressing excitement and caution in the same breath, understand that both reactions are completely justified. The excitement comes from the genuine possibility of witnessing something rare and beautiful. The caution comes from decades of experience with comets that promised much and delivered little, or comets that behaved in ways nobody predicted. But here's what we do know for certain. This comet exists, it's large, it's heading toward the sun, and we have front row seats to watch what happens next. For anyone who remembers the great comets of the past, who looked up at Halley's Comet, or stood in awe of Hale-Bopp stretching across the evening sky, this moment carries a familiar thrill. It's the feeling of anticipation, of knowing that the universe still has surprises to offer, that despite all our technology and knowledge, nature can still stop us in our tracks with something unexpected. And that's where our journey begins, not with answers but with questions, not with certainty but with possibility. Because the story of 6AC4721 isn't finished yet. In fact, in many ways, it's only just beginning. If this kind of cosmic mystery intrigues you, if you want to follow along as this story unfolds over the coming weeks, then hit that subscribe button right now. Drop a comment telling me where you're watching from, because I have a feeling viewers all around the world are going to be looking up at the same sky in the weeks ahead, hoping to catch a glimpse of something spectacular. And make sure to turn on notifications because I'll be bringing you updates as we get closer to that critical April 5th date. This is the kind of story that develops in real time, and you won't want to miss what comes next. So why could we see this comet from such an incredible distance? The answer to that question reveals something fundamental about what we're dealing with, and it's the key to understanding everything that follows. Let me show you exactly what astronomers discovered when they started calculating the size of this cosmic giant. because what they found changed everything about how they're thinking about this comet's chances and its potential to create a truly memorable display. There's a principle in astronomy that sounds simple, but reveals profound truths about the universe. Brightness at a distance tells you size. It's not complicated physics, not some arcane formula requiring advanced mathematics to understand. It's straightforward logic that anyone can grasp, and once you see how it works, you'll understand exactly why astronomers got so excited about this comet. Let's start with that candle flame I mentioned earlier. On a dark night, you can see a single candle from a surprising distance, maybe half a mile if the air is clear and nothing blocks your view. But you'll never see it from 10 miles away, not with human eyes. The light spreads out as it travels, becoming dimmer and dimmer until it's simply too faint to detect. Now, if someone claimed they spotted a light source from 10 miles away in the darkness, you'd know immediately that whatever they saw wasn't a candle. It would have to be something much brighter, much larger, maybe a bonfire, maybe searchlights, maybe a whole building lit up, but definitely not a candle. The same principle applies to comets. When a comet is far from the sun, it receives less solar heating and reflects less sunlight. It's cold, relatively inactive, and if it's small, it essentially disappears into the darkness of space. Previous sungrazers discovered at comparable distances to where we found 6AC4721 were either completely invisible or just barely detectable as the faintest smudges on the most sensitive instruments. They remained hidden until they got much closer, until the sun's heat began working on them, vaporizing their surface ices and creating the glowing cloud of gas and dust that makes comets visible. But 6AC4721 wasn't a faint smudge. It was clearly visible, bright enough that multiple observatories could confirm its presence without difficulty. And that brightness, combined with the distance, told astronomers something crucial. This comet had to be enormous. Think about the moon for a moment. Even when it's in its crescent phase, when only a sliver is illuminated by the sun, you can still see it easily from Earth. Why? Because the moon is large. It has enough surface area that even a partially illuminated portion reflects sufficient sunlight to be clearly visible across the vast distance between Earth and Moon. A much smaller object at the Moon's distance, even if fully illuminated, would be invisible to your naked eye. Size compensates for distance. With 6AC4721, astronomers were seeing the same effect. Even though the comet was far from the sun, even though solar heating was minimal and activity was just beginning, enough surface area was present to reflect sufficient light for detection. The calculation suggested something remarkable. Early estimates suggest this comet might be several miles across, though this remains to be confirmed. That would make it one of the biggest sungrazers ever discovered, potentially rivaling or exceeding the size of historic great comets that created spectacular displays in decades past. Now, you might wonder why size matters beyond simple visibility. After all, a comet is still just ice and rock regardless of how big it is. But size determines everything about how a comet behaves as it approaches the sun, and it's absolutely critical to understanding what might happen to 6AC4721 in the coming weeks. First, size means structural integrity. A large comet has more mass holding itself together through gravity. When it encounters the intense thermal stress of approaching the sun, when one side is being blasted by radiation while the other remains relatively cold, that mass helps prevent the object from simply breaking apart. Smaller comets are fragile. They can split into pieces or crumble completely when subjected to rapid temperature changes. Larger comets have a better chance of holding together, of maintaining their structure even under extreme conditions. Second, size means more material available for solar heating to work with. As a comet approaches the sun, heat penetrates its surface and begins vaporizing the ices trapped within water ice, carbon dioxide ice, and various other frozen compounds accumulated over billions of years in the outer solar system. Those vaporizing materials stream away from the comet, creating the atmosphere called the coma and the tail we see from Earth. A larger comet has more of these materials, which means it can potentially produce a much more dramatic display if it survives to make a close approach. Third, and perhaps most importantly for our story, size gives astronomers hope. Over the decades, they've watched many small sungrazers dive toward the sun, only to vanish completely, destroyed by the intense heat and tidal forces near our star. Those comets never had a chance. They were too small, too fragile, too vulnerable. But the great sungrazers of history, the ones that survived and created memorable displays, were almost always larger objects with enough mass and structural cohesion to endure the hellish environment of the solar corona. So when the calculation suggested 6AC4721 was unusually large, astronomers allowed themselves to hope. Not certainty, never certainty with comets, but genuine hope that this object might be tough enough to survive, bright enough to create a spectacular show, significant enough to join the ranks of legendary comets that people remember decades later. To put this in perspective, consider some previous sungrazers discovered over the years. Most were detected only when they were already quite close to the Sun, sometimes just days before their closest approach. They appeared suddenly as solar heating kicked their activity into high gear, blazed briefly across astronomical images, and then either vaporized or rounded the Sun and faded back into obscurity. They were small, typically measuring a few hundred yards across at most. Many didn't survive their solar encounter. Those that did rarely became bright enough for amateur astronomers to observe, let alone bright enough for the general public to see without telescopes. But 6AC4721 was announcing its presence from a distance where those smaller comets remained invisible. It was like comparing a whisper to a shout, a flashlight to a lighthouse beacon. And that difference, that fundamental distinction in how early and how clearly this comet appeared, told experienced observers that they might be dealing with something genuinely unusual. Of course, size alone doesn't guarantee anything. Comets have disappointed expectations before. There have been large comets that, for various reasons, didn't brighten as expected. Perhaps their composition was different, with less volatile material available for solar heating to vaporize. Perhaps their structure was unusual in ways that affected how they released gas and dust. Perhaps they simply broke apart before they could reach their full potential. The history of comet observation is littered with examples of objects that seemed promising, but ultimately underwhelmed. So astronomers temper their excitement with realism. They acknowledge the possibility, recognize the potential, but refuse to make definitive predictions. They know better. They've been fooled before by comets that seemed destined for greatness, but fizzled into mediocrity. And they've been surprised by comets that seemed ordinary but exceeded all expectations. What they will say is this: based on the early detection, based on the implied size, based on the trajectory calculations showing a very close approach to the Sun, 6AC4721 has the potential to become something memorable. It has the ingredients, the characteristics that historical great comets possessed. Whether it actually delivers on that potential remains to be seen, but the possibility is real and grounded in solid observational evidence. And that possibility, that chance of witnessing something truly rare, is what makes this story worth following. Because opportunities to see a genuinely spectacular comet don't come along often. For many people, particularly those in their 60s, 70s and beyond, the great comets of the past remain vivid memories. Halley in 1986, Hale-Bopp in 1997, and for those fortunate enough to be watching the sky in the mid-60s, the legendary Comet Ikeya-Seki. These weren't just astronomical events, they were moments of wonder that cut through the routine of daily life and reminded people that we live in a dynamic, surprising universe. So as we watch 6AC4721 moving closer to the Sun over the coming weeks, as we wait to see whether it lives up to its promise or falls short, we're participating in that same timeless human experience of looking up and hoping to witness something beautiful. The size calculation gives us reason to hope, the early detection gives us reason to pay attention, and the trajectory, that dangerous plunge toward the Sun's corona, sets up the dramatic question that will determine everything. Will this comet survive? But before we can understand what survival means and what might happen to 6AC4721 when it faces the Sun's full fury, we need to talk about what it actually means to be a sungrazer. Because this isn't just any close approach to our star. This is something far more extreme, far more dangerous, and far more spectacular if things go right. Imagine standing at the edge of a blast furnace, feeling the heat radiating from molten metal that could burn through anything in seconds. Now imagine diving directly into that furnace, passing through its heart where temperatures reach levels that would vaporize rock itself, and somehow emerging on the other side intact. That's essentially what a sungrazing comet attempts to do, and it's a journey that most don't survive. The term sungrazer sounds almost casual, like these comets are just skimming past our star at a respectful distance. But the reality is far more dramatic. A sungrazing comet doesn't stay safely away from the Sun. It plunges directly toward it, diving so close that it actually passes through the Sun's outer atmosphere, a region called the corona, where temperatures soar to millions of degrees and radiation bombards anything foolish enough to venture there. To understand how extreme this is, consider that our planet Earth orbits at a comfortable distance from the Sun, approximately 93 million miles away. At that distance, solar radiation provides warmth for life, drives our weather systems, and gives us light to see by. It's perfectly balanced for our needs. Mercury, the innermost planet, orbits at about 36 million miles from the Sun. Even at that distance, Mercury's surface temperatures can reach over 800 degrees during its day, hot enough to melt lead, and that's still millions of miles away from the Sun itself. A Sungrazing Comet doesn't stop at Mercury's distance. It doesn't even stop at 1 million miles from the Sun's surface. These objects dive to within a few 100,000 miles of the Sun, and some pass even closer, actually skimming through the corona itself. At those distances, the environment becomes unimaginable. The Sun's outer atmosphere, despite being less dense than air, reaches temperatures that defy everyday experience. We're talking about heat that would instantly vaporize any known material, radiation intense enough to strip atoms apart, and magnetic fields powerful enough to tear structures to pieces. And yet some comets survive this journey. They pass through that hellish environment, hold themselves together through forces of extreme intensity, and emerge on the other side still intact. It seems impossible, and in many cases it is. Most small sungrazers simply vanish. They approach, they begin to heat up, they brighten briefly as their surface ices vaporize, and then they disintegrate completely. One moment there's a comet, the next there's nothing but a dispersing cloud of debris. They vaporize completely, but the larger sungrazers, the ones with enough mass and structural integrity, sometimes make it. They lose material, certainly. The outer layers are stripped away by heat and radiation, vaporized into gas and dust that streams away in spectacular tails, but the core remains solid, protected by the very material being sacrificed from the surface. It's like ablative heat shielding on a spacecraft, where outer layers burn away to protect the interior. If the comet is big enough, if its composition is favorable, if it holds together through the worst of the heating, it survives. And that's the question hanging over 6AC4721. Will it survive? This comet is a member of what astronomers call the Kreutz family, a group of sungrazers that all follow similar orbits and likely originated from the breakup of a single large comet centuries or even millennia ago. The Kreutz sungrazers are well known to astronomers. Dozens have been discovered over the years, particularly in recent decades as space-based telescopes have made it easier to detect objects near the Sun. Most of these Kreutz comets are small fragments, the scattered remnants of that ancient breakup. They arrive, they vaporize, and they're gone. But occasionally a larger piece arrives, a substantial fragment that retained enough mass during the original breakup to qualify as a significant object in its own right. These larger Kreutz comets are rare, and when they appear they tend to create memorable displays precisely because they have the size to survive the solar encounter. Based on its early detection and implied size, 6AC4721 appears to be one of these larger fragments. It's not a small chip broken off from the parent body. This is a substantial piece, possibly one of the biggest Kreutz fragments to make a solar approach in decades, and that size gives it a fighting chance. The date astronomers have circled on their calendars is April 5th. That's when 6AC4721 will reach perihelion, the point in its orbit closest to the Sun. At that moment, the comet will experience the full intensity of our star's power. Every second, the Sun converts millions of tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to billions of nuclear bombs. A tiny fraction of that energy will focus on this small, cold visitor from the outer solar system, heating it to temperatures that could melt steel in an instant. What happens during those critical hours around perihelion will determine everything. If the comet is structurally weak, if it's held together more by loose binding than solid cohesion, the thermal stress could cause it to break apart. We've seen this happen with other comets. They approach, they begin to fragment, and by the time they reach perihelion, they've split into multiple smaller pieces or disintegrated entirely. Each fragment is less able to survive than the original object would have been, and the result is often complete vaporization. If the comet is composed primarily of volatile materials that vaporize easily, it might exhaust itself before rounding the Sun. The outer layers would boil away rapidly, and without enough material remaining to protect the core, the entire object could vaporize. This is the fate of many smaller sungrazers. They're simply not big enough to sustain the mass loss and hold together through perihelion. But if 6AC4721 has favourable composition, if its interior contains enough stable material to maintain structural integrity, if it's genuinely as large as the early detection suggests, then it has a real possibility of survival. Not a guarantee, never a guarantee with comets, but a genuine possibility. And if it survives, what emerges on the other side could be something spectacular. You see, the very process that threatens to destroy a sun-grazing comet is also what makes it visible and potentially beautiful. As solar heating vaporizes the surface, gas and dust pour off the comet at tremendous rates. This material forms the coma, the glowing atmosphere around the comet's solid nucleus. It also forms the tail, or more accurately the tail's comets typically develop two distinct tails, one of gas pushed directly away from the sun by radiation pressure, and one of dust particles that curve gently along the comet's orbit. For a large comet making a close solar approach, these effects can become dramatic beyond imagination. The amount of material being vaporized increases exponentially as the comet gets closer to the sun. The tails can stretch millions of miles through space, the coma can expand to dimensions larger than planets, and the overall brightness can increase by factors of hundreds or even thousands. This is what happened with the great sun grazers of history. This is why they became memorable, why people remember them decades later. They were comets that got close enough to the sun to undergo tremendous heating and mass loss, but large enough and strong enough to survive the experience. The combination created displays that, for a brief period, dominated the sky and captured global attention. Will 6AC4721 join those ranks? Will it survive to create that kind of display? Or will it succumb to the sun's power and vanish like so many smaller objects before it? Right now, nobody knows. The comet is still far enough away that conditions remain relatively gentle. It's brightening gradually as solar heating increases, but the real test hasn't arrived yet. The real test comes on April 5th, when the comet passes through the region where the sun's power becomes truly overwhelming. That's when structural weaknesses will reveal themselves. That's when composition will determine fate. That's when we'll discover whether 6AC4721 has what it takes to endure. And here's what makes this particularly compelling. The outcome genuinely is uncertain. This isn't manufactured drama. Nobody's hyping something that's already been decided. The comet's fate remains genuinely unknown, and it will remain unknown until we watch it happen in real time. That's rare in astronomy, where most events can be predicted centuries in advance with incredible precision. But comets, particularly sun-grazers making such extreme approaches, remain stubbornly unpredictable. They surprise us. They confound expectations. They remind us that nature still holds mysteries we can't fully anticipate. For anyone who loves genuine suspense, who appreciates stories where the outcome isn't predetermined, this is your cosmic thriller. Every day as the comet gets closer, as astronomers gather more data and watch its behaviour evolve, we're adding new chapters to a story that won't finish until April. And even then, the story continues, because if the comet survives, we'll watch it emerge from behind the sun and potentially brighten into something Earth-based observers can actually see. But I mentioned earlier that understanding what might happen requires looking at history, at previous sun grazers that face similar challenges. And there's one comet in particular, one legendary sun grazer from decades ago, that provides the perfect comparison for what 6AC4721 might achieve if everything goes right. It's a comet that people still talk about, still remember, still describe as one of the most spectacular celestial displays they ever witnessed. And the parallels between that historic comet and our current visitor are striking enough that astronomers are cautiously allowing themselves to wonder whether lightning might strike twice. If you were alive in October of 1965, if you were old enough to pay attention to the sky and the news, you might remember something extraordinary. Not a satellite launch or a space mission, though those were happening regularly during that era of the space race. Not an eclipse or a meteor shower, though those have their own beauty. No, what happened in October of 1965 was something that hadn't occurred in decades and hasn't really happened since a comet so bright that it became visible in broad daylight, shining near the sun itself like a second solar companion. Its name was Comet Ikeya-Seki, and it remains the gold standard by which all subsequent sun-grazing comets are measured. Two amateur astronomers, working independently in Japan, discovered this comet in late September of that year. It was already relatively bright when they spotted it, which immediately suggested something unusual was approaching. As professional astronomers calculated its orbit, excitement built rapidly. The calculations showed this comet would make an extremely close approach to the Sun, diving through the corona just like other Kreutz sungrazers. But this one was different. This one was large, perhaps several miles across, with enough mass to have a genuine chance of survival. And survive it did, in spectacular fashion. In the days leading up to perihelion, Comet Ikeya-Seki brightened dramatically. Observers with telescopes watched it transform from a faint fuzzy patch to a brilliant object with a developing tail. Those watching knew something special was building. Then came the perihelion passage itself, when the comet dove to within just a few 100,000 miles of the Sun's surface and disappeared into the solar glare. For several hours nobody could see it. The comet was lost in the overwhelming brightness of our star, and during that time uncertainty reigned. Had it survived? Would it emerge on the other side, or had the Sun's power proved too much? Previous sungrazers had vanished during perihelion, destroyed by forces they couldn't withstand. Would this one be different? Then it emerged. And what emerged was something that left observers struggling for words. On the morning of October 21st, people around the world who had been following the predictions went outside before dawn to look for the comet in the eastern sky. What they saw exceeded even the most optimistic expectations. Comet Ikeya-Seki had not just survived, it had become one of the brightest comets in recorded history. Its head shone brilliantly, easily visible to the naked eye despite being near the Sun in the sky. And stretching away from that blazing head was a tail of such incredible length and brightness that it dominated the pre-dawn sky. But here's what made Ikeya-Seki truly legendary. It remained visible even after the sun rose. As daylight filled the sky and stars faded from view, the comet persisted. Observers who knew where to look could still see it. A brilliant streak near the Sun that refused to be washed out by our star's overwhelming light. Imagine that. Imagine being able to step outside during the day, look toward the Sun while being careful not to stare directly at it, and seeing a comet hanging in the bright blue sky. That's not supposed to happen. Only a handful of objects in our solar system are bright enough to be visible during daylight without optical aid. The Sun itself, obviously. The Moon, when it's up. Venus at its brightest if you know exactly where to look. And very, very rarely, a comet that has become so intrinsically bright through either size, activity, or proximity to the Sun that even daylight can't hide it. Ikeya-Seki achieved that status. For several days around its perihelion passage, it was a daylight comet, visible to anyone who looked for it. And in the pre-dawn hours, when the sky was still dark, it was absolutely magnificent. Photographers captured images showing a tail stretching 20 or even 30 degrees across the sky. That's equivalent to 60 moon widths, an enormous expanse of glowing gas and dust streaming away from the comet's nucleus. People who witnessed Ikeya-Seki describe it as one of the most memorable celestial sights of their lives. It wasn't just that it was bright, though it certainly was. It was the combination of brightness, the spectacular tail, the unusual circumstance of seeing it near the Sun, and the knowledge of what this object had just endured. This was a cosmic visitor that had passed through hell and emerged transformed, blazing with reflected sunlight and the glow of vaporizing ices. If you're younger, if you weren't around in 1965 or were too young to remember, try to imagine what this meant for people of that era. This was before the internet, before smartphones, before the constant stream of images from space telescopes and planetary missions. Seeing something spectacular in the sky was a rare and precious experience. When something like Ikeya-Seki appeared, it became a shared cultural moment. People talked about it. Newspapers ran front-page stories with photographs. Parents woke their children early to see it before school. It created memories that lasted lifetimes. Now, here's why this history matters for our current story. Comet 6AC4721 shares several key characteristics with Ikeya-Seki. Both are Kreutz sungrazers, meaning they follow similar orbital paths. Both appear to be large objects, substantially bigger than typical small sun-grazing fragments. Both were detected earlier than usual, suggesting significant size, and both will make extremely close approaches to the Sun, diving through the corona where temperatures and conditions are most extreme. The parallels are striking enough that astronomers who remember Ikeya-Seki, or who have studied it through historical records, are cautiously allowing themselves to wonder whether we might be on the verge of witnessing a similar display, They're not predicting it, the universe has taught them too much caution for that, but they're acknowledging the possibility. Because if 6AC4721 survives its April 5th perihelion passage the way Ikeya-Seki survived in 1965, if it holds together through that hellish environment and emerges intact, if solar heating drives enough activity to create dramatic brightening, then yes, we could be looking at something comparable to that legendary comet. Understand what that would mean. A comet bright enough to be easily visible to the naked eye, a tail stretching across the sky, visible in the weeks after perihelion as the comet moves away from the sun and becomes better positioned for evening viewing. A celestial display that would capture global attention, that would get people to put down their phones and actually look up at the sky, that would create memories lasting decades. That's the best case scenario. That's what could happen if everything breaks right for this comet. And the fact that it's not impossible, that there's historical precedent for exactly this kind of event, is what has astronomers and comet enthusiasts around the world paying close attention. Of course, Ikeya-Seki was 60 years ago. A lot has changed since then, particularly in our ability to observe and study comets. In 1965, astronomers relied on ground-based telescopes and photographic plates. There were no space telescopes, no coronagraphs constantly monitoring the sun's vicinity, no international network of automated survey telescopes scanning the sky every night. Today, we have all of those advantages and more. We can track comets with precision that would have seemed like science fiction in the 60s. We can analyze their composition through spectroscopy, measure their size and rotation, monitor their brightness changes in real time. This means we'll have a much more detailed view of what happens to 6AC4721 than observers had with Ikeya-Seki. We'll watch its approach day by day. We'll see the perihelion passage itself through specialized solar observatories that can detect the comet even when it's lost in the sun's glare. We'll know immediately whether it survives, and we'll be able to track its post-perihelion behavior with instruments that can detect changes invisible to the human eye. In some ways, this makes the experience richer. We'll understand what's happening in much greater detail, but in other ways, it might reduce the mystery and surprise that made Ikeya-Seki so magical for those who witnessed it. In 65, nobody knew exactly what would happen. Predictions were rough, observations were limited, and the comet itself provided surprises at every stage. Today, surprises are harder to come by because we have so much more data, so much more capability to monitor and measure. Still, comets find ways to surprise us. They always have, and 6AC4721, if it lives up to its potential, will create its own kind of magic regardless of how many instruments we point at it. Because there's something fundamentally moving about witnessing a cosmic event like this, something that transcends data and measurements. It's the experience of seeing something ancient and rare, of being connected to the universe beyond our small planet, of sharing a moment with millions of other people who are also looking up and feeling that same sense of wonder. For those who remember Ikeya-Seki, this is a chance to potentially experience that feeling again. For those too young to have seen any of the great comets, it's a chance to understand what previous generations experienced, to create your own memories of looking up and seeing something extraordinary. And for everyone in between, it's simply an opportunity that doesn't come along often, a real possibility of witnessing something genuinely special in the sky. But we're still in the waiting phase. We're still watching, still gathering data, still hoping but not assuming. April 5th remains weeks away, and until that date arrives, until we see what happens when 6AC4721 faces the ultimate test, we won't know whether this comet will follow in Ikeya-Seki's footsteps or carve out its own place in history, whether spectacular or modest. And that brings us back to the present, to what we can actually see right now as we watch this cosmic drama unfold in real time. Because 6AC4721 isn't just sitting still out there waiting for April. It's already changing, already showing signs of activity, already providing clues about its nature and potential. Astronomers are watching closely, interpreting every observation, building their understanding of what this object is and what it might become. So let's talk about what's visible right now, what those observations tell us, and why even the experts are admitting there's so much they still don't know. Every night, at observatories scattered around the world, astronomers are pointing telescopes at 6AC4721. They're taking images, measuring brightness, analyzing the light spectrum, tracking any changes in the comet's appearance. This isn't passive observation. This is active investigation. where each piece of data adds another clue to understanding what this object is and what it might become. Right now, the comet shows clear signs of activity. It's not just a point of light anymore, not just a bare nucleus reflecting sunlight. A coma has formed, that diffuse atmosphere of gas and dust surrounding the solid core. Through telescopes, the comet appears fuzzy, slightly elongated, with a hint of tail development already visible, even though it's still far from the Sun. This is exactly what astronomers want to see, because it confirms the comet is releasing material, that solar heating is beginning to work on its ices, that the process of transformation from dormant ice ball to active comet is well underway. The brightness has been increasing steadily, following a curve that suggests continuing activity as the comet moves closer to the Sun. Every week, observers report that it's grown slightly brighter, that the coma has expanded a bit more, that the tail is becoming more pronounced. These are positive signs, indicators that the comet is behaving as expected for a large, potentially spectacular object approaching the Sun. But here's where things get complicated. Comets are fundamentally unpredictable. Yes, we can observe them. Yes, we can measure their current brightness and track how it changes. But predicting how bright a comet will become, especially one making such an extreme close approach to the Sun, remains more art than science. There are simply too many variables, too many unknowns about composition and structure, too many ways that reality can diverge from expectations. Astronomers use something called absolute magnitude to describe a comet's intrinsic brightness, and they employ various formulas to predict how that brightness will change as the comet approaches the Sun. Based on current observations, the predictions for 6AC4721's peak brightness range widely. Some conservative estimates suggest it might reach naked eye visibility, but remain relatively modest. More optimistic calculations suggest it could become quite bright, possibly rivaling the brightest stars, and at the extreme upper end, if everything aligns perfectly, there are scenarios where it could approach the brightness that Ikeya-Seki achieved. That range of predictions tells you everything you need to know about our current understanding. We simply don't know which scenario will play out. The comet could surprise us by brightening more than expected. It could disappoint by staying dimmer than hoped. It could do something completely unexpected that doesn't match any model or prediction. That's just the nature of comets, particularly ones in circumstances as extreme as a very close solar approach. Part of the uncertainty comes from composition. Comets aren't uniform objects with consistent makeup. They're mixtures of various ices: water ice, carbon dioxide ice, methane ice, and others combined with dust particles and rocky material. The exact proportions of these components vary from comet to comet, and those proportions dramatically affect how the comet responds to solar heating. A comet rich in highly volatile materials will brighten more dramatically and earlier than one composed primarily of water ice. A comet with lots of dust will scatter more sunlight and potentially appear brighter than one that releases mostly gas. We don't have detailed composition information for 6AC4721 yet. Spectroscopic observations can provide some clues, but the comet is still too far and too faint for really detailed analysis. As it gets closer and brighter, astronomers will gather better spectroscopic data, which will help refine predictions. But for now, composition remains an educated guess based on what we know about other Kreutz comets. Structure also plays a critical role. Is the comet a solid, coherent object, or is it more like a loosely bound pile of debris held together by weak gravity? This matters enormously for survival chances and brightness behavior. A solid object can withstand more thermal stress. It's less likely to break apart under the extreme conditions near the Sun, but it might also be slower to release material, which could mean less dramatic brightening. A loosely bound object might release material more readily, potentially creating more dramatic displays, but it's also more vulnerable to breaking apart. Again, we won't know which scenario applies to 6AC4721 until we watch it happen. Astronomers look for signs of fragmentation, watch for sudden changes in brightness that might indicate structural failure, monitor the comet's behavior for any hints about its internal makeup. So far, the comet appears to be holding together nicely, showing steady activity without signs of distress. But the real test hasn't happened yet. There's also the possibility of outbursts. Sometimes comets suddenly and dramatically brighten for brief periods, releasing large amounts of material in unpredictable bursts. These outbursts can happen for various reasons. Perhaps a pocket of highly volatile material suddenly gets exposed to sunlight, or perhaps a structural failure exposes fresh surface. When outbursts occur, They can temporarily boost a comet's brightness by factors of 10 or even 100. They're dramatic, they're exciting, but they're also impossible to predict. A comet might experience several outbursts during its approach, or it might never have any at all. So as astronomers watch 6AC4721 week by week, they're looking for these various clues. Is the brightness increasing smoothly, or are there variations that suggest underlying instability? Is the tail developing normally, or are there unusual features that might indicate fragmentation? Is the colour of the reflected light changing in ways that reveal composition? Every observation adds information, but the complete picture won't emerge until we're much closer to that critical April 5th date. For anyone watching this unfold from outside the professional astronomical community, it's a bit like watching detectives gather clues in a mystery where the ending hasn't been written yet. We have pieces of information, we can make educated guesses, we can hope for certain outcomes and prepare ourselves for others. But we can't skip ahead to the conclusion. We have to wait and watch as events unfold naturally, as the comet continues its journey toward the Sun, and toward whatever fate awaits it there. And that's actually part of what makes this compelling. We're not being told a story that's already finished. We're living through it in real time, discovering the plot alongside everyone else. The outcome genuinely is uncertain, and it will remain uncertain until it actually happens. That's rare in our modern world where so much is predictable, where algorithms can forecast behavior and outcomes with disturbing accuracy. Here, nature still has the final word, and nature isn't revealing its intentions until the moment arrives. What we do know is this: 6AC4721 is currently behaving like a comet with potential. It's showing activity, it's brightening appropriately, it's developing the features we'd expect from a large object approaching the Sun. The early signs are positive, but early signs don't guarantee anything. The real questions won't be answered until perihelion, until that moment on April 5th when the comet faces maximum solar heating and either survives or doesn't, either brightens dramatically or remains modest, either fulfills the hopeful predictions or teaches us something new about how sungrazers behave. So we watch, we wait, we gather more data with each passing night, and we prepare ourselves mentally for the range of possible outcomes, from disappointment to amazement, from vaporization to spectacular success. Because that's all we can do at this point: stay patient, remain curious, and trust that whatever happens will teach us something valuable about these ancient visitors from the outer solar system. Speaking of possible outcomes, maybe it's time we looked at those scenarios in more detail. What could actually happen to this comet? What are the realistic possibilities we're facing as April 5th approaches? Let me walk you through 3 distinct scenarios that bracket the range of likely outcomes, from worst case to best case, and explain what each would mean for anyone hoping to catch a glimpse of this cosmic visitor. Let's talk about what might actually happen. Not wild speculation, not manufactured hype, but realistic scenarios grounded in what we know about comets, about sungrazers specifically, and about how objects behave when subjected to the extreme environment of the inner solar system. There are 3 basic outcomes we're facing, and understanding each of them helps prepare you emotionally for whatever reality delivers. The first scenario is complete vaporization. It sounds dramatic, and in some ways it is, but it's also a common fate for smaller sungrazers. In this scenario, as 6AC4721 approaches the Sun and conditions become increasingly extreme, the comet begins to lose structural integrity. Maybe there's a weak point in its composition, a region where the binding isn't strong enough to resist the thermal stress. Maybe the outer layers ablate faster than expected, exposing internal structure that can't handle the heat. Maybe tidal forces, the difference in gravitational pull between the sun-facing side and the far side of the comet, exceed the object's ability to hold itself together. Whatever the specific mechanism, the result is the same: the comet breaks apart. Initially, this might manifest as a splitting event where the nucleus divides into 2 or more fragments. This actually happens fairly often with comets, and it's not necessarily fatal. Sometimes the fragments continue on similar paths and behave almost like separate comets, each experiencing its own evolution. But with sungrazers making such close approaches, fragmentation is usually the beginning of the end. The fragments are smaller than the original object, which means they're more vulnerable to further disruption. They have less mass to hold them together and less material to protect their cores from solar heating. As these fragments continue toward perihelion, they experience accelerating mass loss. The heat vaporizes their surfaces at increasing rates. They brighten briefly as more and more material is released, but this brightening is the glow of destruction, not the sign of a healthy, surviving comet. and then, somewhere in the final approach or during the perihelion passage itself, they simply vanish. One moment there's a comet, or fragments of a comet, visible in solar observatory images. The next moment there's nothing but a fading cloud of dispersing debris. The comet has been completely destroyed, vaporized by the sun's power, its material scattered into space to slowly disperse and become part of the interplanetary medium. If this happens to 6AC4721, it would certainly be disappointing to anyone hoping for a spectacular display. But it wouldn't be unusual or unexpected. Many sungrazers meet this fate, even relatively large ones, and from a scientific perspective it's still valuable. Astronomers would learn about the comet's structure and composition from watching how it broke apart. They'd gain data about the forces required to disrupt such an object. They'd add another data point to the statistical understanding of sungrazer behavior. It's not the outcome anyone hopes for, but it's a legitimate possibility that we need to acknowledge. The second scenario is survival but modest brightness. This is perhaps the most likely outcome based on statistical averages of sun-grazing comets. In this scenario, 6AC4721 holds together structurally. It passes through perihelion, endures the extreme heat and radiation, loses a significant amount of material from its surface, but maintains enough cohesion to emerge on the other side as a recognizable, intact object. The comet survives. However, in this scenario the brightening doesn't reach spectacular levels. Maybe the composition isn't favorable for dramatic activity. Maybe the comet is rotating in such a way that limits how much surface area gets heated at any given time. Maybe it's just not releasing material as abundantly as optimistic predictions hoped. Whatever the reason, the result is a comet that's certainly visible to those with telescopes, that's interesting to study and track, but that never becomes bright enough for casual naked eye viewing from typical suburban locations. This would still be a success in many ways. A sungrazer that survives such a close solar approach is scientifically fascinating. Astronomers would be able to study how the comet's activity evolves after perihelion, how its orbit changes due to the momentum of all that released material, what happens to its brightness and tail structure as it moves away from the sun. For dedicated comet enthusiasts with binoculars or small telescopes, it would provide weeks of interesting viewing opportunities, and it would add valuable data to our understanding of large Kreutz comets and their survival capabilities. But let's be honest, for the general public, for people who don't have telescopes or who aren't deeply interested in astronomy as a hobby, this scenario wouldn't create much excitement. It would be a success for specialists, but not a cultural moment that captures widespread attention. Most people wouldn't see it, wouldn't hear about it beyond perhaps a few articles in science sections of news websites, and wouldn't remember it years later as a significant event. Which brings us to the third scenario, the one that has astronomers cautiously allowing themselves to hope: spectacular brightening. This is the scenario where everything goes right, where 6AC4721 not only survives but becomes genuinely brilliant. In this version of events, the comet holds together structurally, its composition proves favourable for abundant activity, and the close solar approach drives massive material release that creates dramatic brightening. Imagine it this way: the comet dives toward perihelion, and as it does, solar heating increases exponentially. The surface begins to vaporize rapidly, releasing gas and dust at tremendous rates. The comet expands to enormous size, possibly becoming larger than the sun itself in angular diameter. The tail, or tails, stream away from the comet for millions of miles, creating a spectacular structure that catches sunlight and glows brilliantly. Around perihelion, the comet might become bright enough to be visible in broad daylight near the sun, just as Ikeya-Seki was. Observers who know where to look, who understand how to view objects near the sun safely, would see a brilliant light that has no business being visible against the blue sky. And then, as the comet emerges from behind the sun and becomes better positioned for viewing in the dawn or evening sky, it blossoms into something truly memorable. In the weeks following perihelion, this spectacular scenario would give us a comet easily visible to the naked eye from even light-polluted locations. The tail would stretch across significant portions of the sky, creating a structure visible to anyone who stepped outside and looked up. Photographs would show details invisible to the eye streamers in the tail, colour variations, the bright central condensation where the nucleus resided. The comet would dominate astronomy news, appear on front pages, trend on social media, and create those precious shared moments where people from different backgrounds and interests all pause to look at the same celestial object and feel the same sense of wonder. This scenario isn't just fantasy. It's what happened with Ikeya-Seki. It's what happened with other great comets throughout history. The precedent exists, the physics allows for it, and based on the early signs, the large implied size, the early detection, the favourable trajectory 6AC4721 has at least the potential to follow this path. And this is critical potential doesn't guarantee outcome. Comets have disappointed expectations before, sometimes dramatically. There have been comets that seemed destined for greatness based on early observations that had astronomers confidently predicting spectacular displays that generated widespread media coverage and public excitement, and that ultimately underwhelmed. Perhaps the most famous recent example was Comet Ikeya, which in late 2013 seemed poised to become a brilliant object. Early observations suggested it was large and active. Predictions ranged from very bright to potentially spectacular. Media coverage built up public expectations, and then Ikeya approached the Sun and disintegrated completely. It didn't survive. People who had been told to expect something amazing saw nothing at all. That experience taught astronomers to be more cautious with their predictions, more careful about managing public expectations. They learned that even when signs seem positive, even when models suggest spectacular outcomes, reality can deliver something entirely different. More recently, two other sungrazers, C2024 S1 in October 2024 and C2024 G3 just last month in January 2025, both disintegrated before reaching perihelion, reminding us once again that even promising comets can fail to survive their solar encounters. Comets are humbling that way. They remind us that nature doesn't care about our predictions or hopes. Nature follows its own rules, and sometimes those rules produce outcomes we didn't anticipate. So when astronomers talk about 6AC4721 today, they balance optimism with caution. They acknowledge the potential for something spectacular while refusing to promise that outcome. They explain the favourable signs while noting the many ways things could go differently. They want people to pay attention, to watch this story unfold, to have realistic hope for something beautiful, but they don't want to create expectations that might lead to disappointment if reality delivers a more modest result. Where does that leave us? It leaves us with genuine uncertainty and genuine possibility existing simultaneously. The comet could vaporize, and if it does, that's scientifically interesting even if disappointing for spectacle. It could survive but remain modest, providing weeks of interest for telescope users without capturing broader public attention. Or it could survive and brighten dramatically, creating the kind of memorable display that happens, perhaps once or twice in a human lifetime. All three scenarios are legitimate possibilities. The range isn't artificially wide to hedge bets, it genuinely reflects our limited ability to predict cometary behaviour under extreme conditions. And that uncertainty, while perhaps frustrating for those who want clear answers now, is actually part of what makes this story compelling. Because we get to watch it unfold in real time, we get to see which scenario reality chooses, we get to participate in the suspense and discovery. In the meantime, while we wait to see which future 6AC4721 will deliver, there are practical questions to consider. If the comet does become visible, how will you actually see it? What do you need to know to maximise your chances of catching a glimpse? When should you look, and where, and what should you expect? These are important questions, and they deserve thoughtful answers, because the difference between seeing a comet and missing it often comes down to simple, practical knowledge about viewing conditions and timing. Let's talk about the practical side of this story, because understanding what might happen is only part of the experience. Actually participating in it, actually seeing this comet if it becomes visible, requires knowing when to look, where to look, and what kind of conditions give you the best chance of success. And I want to make sure you have that information, because if 6AC4721 does put on a show, I want you to be able to see it. Right now, in late January, the comet is still too faint for casual observation. You'd need a fairly large telescope and dark skies to see it, along with knowing precisely where to point that telescope. This is the domain of dedicated amateur astronomers and professionals who have the equipment and expertise to track faint objects. But that will change as we move through February and into March. By mid-February, observers with larger amateur telescopes should be able to spot the comet without too much difficulty, particularly from dark sky locations away from city lights. It will still appear faint, probably requiring averted vision and patience to see, but it should be accessible to those with 8-inch or larger telescopes. By late February, smaller telescopes might begin to show it, and the comet's increasing brightness should make it easier to locate. March is when things could start getting interesting for more casual observers. If the comet is following an optimistic brightness curve, by mid to late March it might become visible in binoculars. Not obvious, not jumping out at you, but findable if you know where to look and have reasonably dark skies. This is the point where more people can start participating in the experience without needing specialized equipment. Of course, all of this assumes the comet is still intact and brightening as hoped. Remember, we won't know for certain how bright it will become until we actually see it happen. These timeline predictions are based on current observations and optimistic models, but reality could deliver something different. The comet might brighten faster than expected, or slower, or not at all if something goes wrong structurally. Then comes April, specifically April 5th, the date circled on every comet enthusiast's calendar. This is perihelion, the moment of closest approach to the Sun, and this is where the viewing situation becomes both exciting and challenging. Around perihelion, if the comet brightens significantly, it might theoretically become visible to the naked eye. But here's the critical challenge: it will be extremely close to the Sun in the sky, less than 1 degree of separation, making ground-based observation exceptionally difficult and potentially impossible for most viewers. The Sun's overwhelming brightness makes it extremely difficult to see anything near it, and attempting to observe objects near the Sun without proper precautions can damage your eyes permanently. You cannot, absolutely cannot stare at the Sun or near the Sun with unprotected eyes. If the comet becomes bright enough for daylight visibility, the only safe way to observe it is by blocking the Sun itself. Hold your hand out to block the Sun from your direct line of sight, or position yourself so that a building or tree blocks the Sun. Then, with the Sun safely blocked, scan the area around it looking for the comet. Even then, be extremely careful. Any accidental glance at the Sun can cause serious damage. This kind of observation requires caution and common sense. During perihelion itself, the best views will likely come from space-based solar observatories like SOHO, which can observe comets even when they're lost in the Sun's glare. For most ground-based observers, the better viewing opportunity will come in the days and weeks after perihelion, assuming the comet survives. As it rounds the Sun and begins moving away, it will gradually become better separated from the Sun's glare, transitioning from extremely difficult daylight viewing to easier dawn or dusk observation. By mid-April, if the comet has survived and brightened well, it should be visible in the dawn sky before sunrise, low on the horizon in the east. This is when observers at all levels can participate. Early morning, perhaps an hour before sunrise, head outside or find a location with a clear view of the eastern horizon. The sky will be twilight, not fully dark but not bright daylight either, and there, if we're fortunate, you might see a comet. How obvious it will be depends entirely on how bright it became and how much tail development occurred. Best case, it's an unmistakable object stretching across the dawn sky. Modest case, it's a fuzzy spot with a small tail. Visible but requiring dark skies and attention to notice. As April progresses into May, the comet will climb higher in the dawn sky, making it easier to observe but also moving farther from the Sun, which typically means decreasing brightness as solar heating diminishes. There's often a sweet spot in the weeks following perihelion, where the comet is still relatively bright from recent solar heating, but positioned in the sky for comfortable viewing. That sweet spot, if it arrives for 6AC4721, will probably be late April through early May. Now here's something important to understand about viewing conditions. If you live in a city with significant light pollution, if you're surrounded by bright lights that wash out the night sky, you'll have a harder time seeing the comet unless it becomes very bright. The contrast between the comet and the background sky diminishes when that background is already bright from light pollution. Faint details like extended tail structure will be invisible. You might see the brighter central portion, but the full majesty of the comet could elude you. If possible, plan to travel away from city lights for your viewing attempts. Even just 30 minutes away from urban centres can make a dramatic difference in what you can see. Dark sky locations where the Milky Way is clearly visible on moonless nights will show you everything the comet has to offer. The difference between observing from a dark site versus a light-polluted area is like the difference between watching a movie on a tiny phone screen versus a theatre screen. The content is the same, but the experience is vastly different. Also consider the moon's phase. A bright moon can wash out faint celestial objects just as light pollution does. In late April, check lunar phases and try to plan your observations for nights when the moon is either not up or is in a crescent phase. The darker the sky, the better your chances of seeing all the subtle details a comet can offer. For those in the southern hemisphere, viewing geometry will be different. Depending on your latitude, the comet might be better or worse positioned than for northern observers. I won't go into all the technical details here, but if you're serious about observing, check astronomy websites or apps that can show you exactly where the comet will be in your sky at your location. These tools can calculate rise and set times, altitude above the horizon, and optimal viewing windows specific to where you live. And here's something I want to emphasize. This is a shared experience. All over the world, if this comet becomes visible, people will be looking up at the same time, seeing the same object, feeling the same wonder. There's something profoundly moving about that. In our fragmented world where we often feel isolated or divided, a comet visible to millions of people simultaneously creates a moment of unity. We're all just humans on a small planet, watching an ancient visitor pass through our solar system, connecting us to the cosmos and to each other. Consider sharing the experience with others. If you have grandchildren, wake them early one morning to see the comet. They might not remember all the details years from now, but they'll remember that you thought it was important enough to show them, that you wanted to share something beautiful with them. If you have neighbours who might be interested, mention it to them. Maybe organise a little viewing session where you all head out together in the pre-dawn hours. Community makes these experiences richer, and document what you see, even if it's just writing down your impressions. Photography has become easier with modern smartphones, and you might be able to capture at least something of the comet even without specialised equipment. But even if you don't take pictures, write about the experience. Describe what you saw, what you felt, what the weather was like, who you were with. These personal records become precious years later, small windows back to a moment that felt special at the time. We're currently 75 days away from perihelion. That's enough time to prepare, to plan, to make sure you're ready if the comet delivers on its potential. It's also enough time for the situation to evolve, for our understanding to improve, for predictions to be refined. I'll be following this story closely, and I encourage you to do the same. Check astronomy websites periodically for updates on the comet's brightness and behaviour. Watch for news about whether it's meeting expectations or surprising observers. Stay engaged with the developing story so that when the critical moments arrive, you're informed and ready. Whatever happens, whether we get a spectacular show or something more modest, this is your opportunity to participate in a rare cosmic event. Opportunities like this don't come along often. Genuinely bright comets appear perhaps once or twice per decade, and truly spectacular ones are even rarer. This might be your best chance in years, perhaps in the remainder of your lifetime, to see something truly special in the sky. Don't let it pass by unnoticed. Pay attention, make plans, and if the comet becomes visible, make the effort to see it. You won't regret it. But beyond the practical details of when and where to look, beyond the technical information about brightness and visibility, there's a deeper question worth considering. Why does any of this matter? Why should we care about a chunk of ice and rock passing through our solar system? What makes a comet worth our attention and wonder? Those questions deserve thoughtful answers, because the meaning we find in experiences like this shapes how we remember them and what they contribute to our lives. There's something profoundly human about looking up at the sky and finding meaning in what we see there. We've done it for thousands of years, across every culture, in every era. The stars, the planets, the occasional spectacular visitors like comets, they've always held significance beyond mere scientific curiosity. They've been omens and inspiration, sources of wonder and reminders of our place in the larger cosmos. And that hasn't changed, even in our modern age when we understand so much more about what these objects actually are. When a bright comet appears, it cuts through the routine of daily life. For a brief period, something happens in the sky that demands attention, that gives us permission to pause and simply look up. In our contemporary world, where so much competes for our attention, where screens constantly demand we look down rather than up, a bright comet is a gift. It's a reminder that the universe is still here, still dynamic, still capable of surprising us with beauty. For those who've lived 6, 7, 8 decades or more, you've seen enormous changes in how we relate to the sky. You might remember a time when the Milky Way was visible from your backyard, when the night sky was genuinely dark and filled with stars. You might remember looking up more often simply because there was less competing for your downward gaze. You've witnessed the gradual brightening of our nights as light pollution spread, the the gradual diminishment of that connection between humans and the cosmos that once felt natural and constant. A bright comet, if 6AC4721 becomes one, is a chance to reclaim some of that connection. It's an object bright enough to overcome light pollution, conspicuous enough that even in our distracted age people notice it. And for those few weeks when it's visible, the sky matters again to people who might have stopped paying attention years ago. There's also something valuable about witnessing rare events, about being able to say you were there when something special happened. Not for bragging rights, though that's natural enough, but for the sense of participation in the ongoing story of human observation and wonder. When you saw Halley's Comet, you joined a tradition stretching back centuries of people who watched that same object appear and disappear on its predictable schedule. When you saw Hale-Bopp, you shared an experience with millions of people around the world who also looked up during those months in the late 90s. These become touchstones, reference points in your personal history and in cultural memory. If 6AC4721 becomes a great comet, if it creates the kind of display we're hoping for, you'll have another of those touchstones. You'll remember where you were, who you were with, what it looked like in your particular sky. And years from now, when someone mentions the comet, you'll have that memory to share. You were there, you saw it, you were a witness, and let's acknowledge something else, something that might feel uncomfortable but is worth saying honestly. For those in their later years, opportunities to see truly great comets are limited by simple actuarial reality. Spectacular comets appear unpredictably, sometimes with decades between truly memorable displays. The next genuinely great comet after this one might not arrive for 10, 20, 30 years. We can't know when it will come. Which means this might be your last opportunity to see something like this. Your final chance to stand under a sky graced by a bright comet and feel that particular kind of wonder. That's not meant to be morbid or depressing, it's simply honest. And that honesty makes this moment more precious, not less. If this is potentially your last chance to see a great comet, doesn't that make it more important to pay attention? Doesn't it make the effort to actually observe it more worthwhile? Not everything in life offers second chances. Sometimes we get one opportunity, and what we do with it determines whether we later feel grateful for the experience or regretful about missing it. Of course, all of this assumes the comet delivers on its potential. If it vaporizes or remains modest in brightness, then these grand thoughts about meaning and witnessing might feel overblown. But even the modest outcomes, even the scenarios where 6AC4721 doesn't become the spectacular object we're hoping for, have their own value. We still get to watch a cosmic drama unfold. We still get to participate in the scientific process of observation and discovery. We still get to experience that sense of anticipation and shared attention as people around the world follow the same story. And frankly, the uncertainty is part of what makes this meaningful. We live in a world where so much is predictable, calculated, known in advance. The stock market has algorithms, weather has forecasting, entertainment has algorithms predicting what you'll want to watch next. But a comet approaching the sun doesn't care about our predictions. It will do what physics and its own nature dictate, and we can't skip ahead to the ending. We have to wait and see. That's refreshing in its own way, a reminder that nature still holds surprises, that some things remain genuinely uncertain until they happen. So regardless of outcome, regardless of whether April 5th brings spectacular success or disappointing failure, paying attention to this story has value. Following along, checking for updates, planning your viewing strategy if the comet becomes visible, these activities connect you to something larger than daily routines. They remind you that you live on a planet orbiting a star in a dynamic solar system, that ancient objects still visit from the outer darkness, that the universe around you is not static but constantly changing. For anyone feeling that life has become routine, that one day blends into another without variation or surprise, a comet offers a break in the pattern. It gives you something to look forward to, something to watch develop, something to share with others who care about the same celestial event. That's not nothing. That's actually quite valuable, particularly in times when genuine shared experiences feel rare. I want to thank you for staying with me through this journey, for taking the time to understand what makes 6AC4721 significant, what might happen to it, and why it's worth your attention. An hour is a considerable investment of your time, and I'm grateful you chose to spend it exploring this story with me. I hope you feel better prepared now to follow this comet's progress, to understand what you're seeing in the updates you'll encounter, and to make informed decisions about observing if the opportunity arises. This isn't the end of the story, of course. We're still in the early chapters, still waiting for the climax on April 5th, still uncertain about how it all resolves. I encourage you to return periodically for updates as the critical date approaches. I'll be following this closely, and if significant developments occur if the comet begins behaving unexpectedly, if brightness predictions change dramatically, if something remarkable happens, I'll share that information so we can all stay informed together. In the meantime, look up occasionally. Even before the comet becomes visible, even during these waiting weeks, take a moment now and then to simply observe the sky. Notice how it changes from season to season, how different stars become visible, how the moon moves through its phases. Rebuild that connection with the cosmos that modern life tends to erode. Practice the habit of looking up, so that when the moment arrives, when 6AC4721 potentially becomes visible, you're already comfortable with the process of observing the sky. And remember, whatever happens, whether we witness something spectacular or something modest, whether the comet survives or vaporizes, we're part of a long tradition of humans who have looked up, noticed celestial events, and found meaning in them. That tradition stretches back thousands of years, and it will continue long after we're gone. But right now, in this moment, we're the ones watching. We're the ones who get to see what happens next. That's a privilege, and it's one worth honouring by paying attention, staying curious, and remaining open to wonder. The universe is still out there, still dynamic, still capable of surprise, and for the next 75 days, we get to watch one small piece of that ongoing cosmic drama as it unfolds. Let's not miss it.